So interior angles, again, we were measuring that last time with the pattern block angles. This time we want to add up all of the inside angles. And so I need to write some stuff down for this. I actually want that previous one here. Good. Push the buttons in the right order. There we go. So I'm not worried about the explanation at the moment. I just want to know what some of these angles are to help answer the next activity questions. So conclusions I have now. Coming up any second. There we go. That this one right here, there's just one obtuse angle. And by one, I just mean they're all the same. So that angle is the same as that angle, is the same as that angle, and so on around here. And that one obtuse interior angle, we figured out earlier, is 120 degrees. Now, in the next activity, I'm looking for the sum of all the interior angles. So this hexagon right here has 6 angles that measure 120. So I just have to figure out what 6 times 120 is. So that would be 600 plus 120, which is 720 degrees for that one. This one right here, so this again is a hexagon. I'm wondering, do all hexagons have 720 degrees when we add up their angles? We'll check that out. This one right here is a quadrilateral. And earlier we noticed that we have these 2 obtuse angles, and then we have these 2 acute angles. So the obtuse, we figured, was 120 degrees, like the top of this hexagon. And these acute ones were half of that. 60 degrees. So I have 120 here, 120 there, 60 here, and 60 there. So that's what, 120, 240, 360 degrees. So the sum for a quadrilateral, at least this quadrilateral, is 360 degrees. This is also a quadrilateral. And we figured that that angle right there, different color, that angle right there was 120. This angle right here was 60. So there's another 120 there and a 60 there. So that's pretty much the same as this one above, just they're in a different order. So again, I still get that it is a quadrilateral. And it also has 360 degrees when I sum the interior angles. Better name for this quadrilateral was a trapezoid, the red one. And this trapezoid's even specialer because this side right here matches that side along with the angles. So this is also, it's an isosceles trapezoid. I should have those in the other order. Oops. This one right here is a rhombus. Reminder of what makes it a rhombus, that it has 1, 2, 3, 4 congruent sides, makes it a rhombus. Here, equilateral triangle. It's also equiangular, and each angle is 60 degrees. And so this is a triangle, and this particular triangle had 3 times 60 degrees, for a total of 180 degrees inside. Square. So I'm just using the previous activity to warm up to the new one here. Reminder, this is a square. It's also a quadrilateral. And it has just a whole bunch of 90-degree angles. 90, 90, and we put 4 of them together to double check that that worked out. And so 4 times 90 is going to be 360. this one right here had an acute angle, write that down, of, let's see, that was 30 degrees is my recollection, because it was half, yeah, it was half of this 60-degree angle here, that's correct. And then this angle right here, we figured out was a combination of that angle there and this 120 angle degree up there. And so the obtuse angle was 150. Obtuse. So we have, let's clean this up a little because it's harder to write in, it's smaller. Oh, that is not an eraser. That's the eraser. So this was 30, 150, 150, and 30. 150 and 150 is 300, 30 and 30 is 60. So this particular rhombus that is also a quadrilateral had an interior angle sum of also 360. So far, every quadrilateral I made, right, this sucker right here is a quadrilateral, this sucker right here is a quadrilateral, quadrilateral, quadrilateral. Every one of them added up to 360 degrees. So is it going to be true that every hexagon has 720 degrees? Well, we're going to try to build a new hexagon and see what happens. So let's get back here to the next activity. So we want to find the sum of the interior angles for each of the polygons below. And again, kind of thing to go on here is 360 degrees is one revolution around a circle. And we also have triangles and parallel lines to play with. So there's all kinds of things we can use to try and figure this out. And my recommendation was to use the pattern blocks to do it, but I'm also going to grab GeoGebra to help me do it too. So let's go and clear this screen. Yes, let's clear everything. And I'm going to make a new shape here. Let's see what happens if I put two of these together. How many sides does this have here? 1, 2, 3, 4, 5, 6. Is that really true? So starting right here, 1, 2, 3, 4, 5, 6. This right here is a hexagon. So let's play around with it and figure out what we got. So I'm going to make my best sketch of that sucker. So let's see, we had this rhombus type shape here. Ooh, come on, good. How about like that maybe? So here's one rhombus, and then I stuck another rhombus on it, and it looks something like that. And this is a hexagon, and I'm making believe, to the best of my artistic ability today, I think I need to try that again. Let's see, what if I go with the straight line tool? Like that. Slightly better. Okay, we're going to go with that one instead. So I'm taking two of those pattern block rhombuses and sticking them together. And again, I just want to verify that this is a hexagon. So starting right here, I have 1, 2, 3, 4, 5, 6 sides. And we're kind of ignoring, this is not an edge. I made a new shape, so I'm going to make that a dotted line there. And what do I know about this shape? Well, I know a lot of the angles. I know that this is 60 degrees there, and that's 60 degrees there. That's 120, that's 60, that's 120, that's 120, that's 60, and that's 60. So now this is an interior angle right there. So use a different color, let's use green. Interior angle. So there's an interior angle here that's 120. Another 120 interior angle. a 60-degree interior angle. This one has a giant interior angle of 240, 60. And another, ooh, that's not 60, that's a 120, isn't it? Did I mislabel anything else? So let's see, 120, 120, 60, 240, 60, and then another 120. 1, 2, 3, 4, 5, 6 angles, right? This is a hexagon. And if I add up all those interior angles, what do I get? A bunch of zeros, and then I get 2, 4, 6 is 10, 14, 20, 2, carry the 2, 2, 3, 4, 5, 6, 7, 720 degrees. That's the same as that regular hexagon we had earlier. Regular hex. Try to look more like this here. My drawing is crap today. Well, that's a little better. And this one, since it's regular, had 120 all around because it's equiangular. So again, this one had an interior angle sum of 720 degrees also. So we have two different hexagons. They seem to have an interior angle sum of 720. Triangles I played around with last class in the videos. An interesting thing about triangles, and this is in the book, so I don't think I'll reproduce it, but if you take any particular triangle, so you randomly make some triangle, I can't really show this on this board very well. Let's say this is my triangle right here. And you make 3 copies of this triangle, and let's say we call this angle right here angle X, and this angle right here angle Y, and this angle right here angle Z. You make 3 identical copies of it and you stick them together so that at a point you have angle Y, angle X, and angle Z. What you're going to find is those 3 angles, when you put them together, make a straight angle. So in general, for a triangle, the interior angle sum is always 180. And if you can get kids to cut 3 identical triangles, which is kind of hard, but not too hard, you can kind of demonstrate that with kids that can pull that stunt off. So the interior angle sum of any triangle is always 180 degrees. And in the book and in Khan Academy, they go over another way to view why that is so, and I'll just leave it up to you to check that out. But this is something that I can exploit with other figures. And I'll show you how to exploit this fact right now. So I am going to redo this shape right here using the idea of the triangles. So I'm going to put this on a new page, and I am going to, I think, grab a screenshot so I don't have to embarrass myself by trying to redraw that again, since I'm struggling to draw today. So the way to exploit the idea that a triangle has 360 degrees within it is to take a figure, pick a vertex. So I'm going to use triangles from one vertex. So what that means is from one vertex, what you're going to do is you're going to connect adjacent vertices, opposite vertices. So remember, a vertex is adjacent to another if they're connected by an outside edge. There is no outside edge connecting this vertex here to that one. So I'm going to draw it in. This one's already drawn, but I'll redraw it. And then this one right here. So this vertex right here was already connected to this one and this one, so there was no point in redrawing that. So I'm only connecting opposite vertices. That's called a diagonal. So anytime you take, you connect one vertex to a non-adjacent vertex, you make a diagonal. And that diagonal connects to an opposite vertex, which is a vertex that's not adjacent. Now, when I do that, so I use, I guess I didn't state that very well. I use triangles from one vertex by drawing diagonals. And it's important that you only focus on one vertex when you do that, otherwise you get a mess. So the result of doing that is I've now dissected this shape into 1, 2, 3, 4 non-overlapping triangles. So that's the result. Dissected this polygon into non-overlapping triangles. Now, who cares? Well, we know that each of these triangles contains 180 degrees. That's a fact about any triangle. This shape is made up of 4 non-overlapping triangles, and those triangles make up its interior angles, right? There's one of them there. These 2 triangles together make that angle. These 2 triangles together make that angle. These 2 triangles make that angle. This triangle contains that one right there. Let me pull this. Oop, just for that green line to go away. And then these 4 triangles together make that last big angle right there. And I have 4 triangles, right? 4 times 180 degrees of interior angles. Let's see, that's going to be 4 times 100 is 400. 4 times 80 is 240. Is that right? No. 4 times 80 is 320. That gives me 720 total, which I knew a different way. My point is there's many ways to go about this. So let's try something else. What do we got here? Back to the activity. Quadrilaterals, we've drew 4 of those on the previous activity. Oops, previous activity back here. And each of those 4 was made up of 360 degrees. Okay, so that's good. So we have a lot of evidence that the interior angle sum for a quadrilateral should be 360. We haven't done any pentagons. We got to do that next. Hexagon, we've done 2 different hexagons, a couple of different ways, and got 720. Oh, we have a guest. Amy's here. Hi, Amy. We are going over activity 10.2b.
Awesome.
And there are other recordings already out there about them. We're just doing it together because it's more fun.
Okay, sounds good.
All right, so let's get a little more organized. So now I'm just kind of playing around based on the last activity. So we are looking at interior angle sums. And starting with triangle, right, which has 3 edges, 3 angles, and then quadrilateral, four angles. Pentagon is what we got to play with next. 5 angles. We just did a couple of hexagons. We'll do another just to make sure. 6 was next on my list. Heptagon, octagon. Heptagon is a 7-sided polygon, and octagon, hopefully everyone knows, is an 8-sided. Octagon, 8-sided. And then we're going to kind of generalize to any number of sided gon. So n-gon could be an octagon or a pentagon, but it could be a 12-sided polygon. So we're going to try and come up with a formula for any n sides or n angles. So let's play with pentagon next. But to summarize, for a triangle, we know it's 180 based on a couple of theories. Quadrilateral, we have 4 examples that show 360 degrees so far. We don't know pentagon yet, but we did just find 2 examples of hexagons that had 720 degrees interior. All right, so I'm going to go and build a pentagon. So I'll do it a couple different ways. I'm going to start with my pattern blocks here and see if I can make myself a pentagon. The easiest one I can think of for a pentagon is a little house. So starting at the top vertex here and going around clockwise, I have 1, 2, 3, 4, 5 sides. I think I can redraw that one. So new page for my pentagons. So I'm not worried about having a regular pentagon. I just made this one right here, my little house shape. And that was made up of this equilateral triangle. And from my previous work, I know this equilateral triangle has 60 degrees up there, and 60 degrees there, and 60 degrees there. And I know my square has 90, 90, 90, and 90. And so when I put all that together, right, I have this top angle, which is 60 degrees. I have this angle right here, which is 60 and 90, or 150. This bottom one, 90. This bottom one, 90. And this big one on the edge there is another 60 and 90, or 150. So for this pentagon, if we add up all the interior angles, bunch of zeros, and then 6 and 5 is 11, and 9 is 20, 29, and 5 is 34. Carry that 3, 4, 5. 540 degrees in this pentagon. Okay, then the question is, do all pentagons have 540 degrees in them? And the answer is, I don't know. Let's take a look at another one. So can I build one a different shape than this one? Let's see. This is a hexagon there. What if I give it a hat? What does that make? This is now one continuous edge. So I have 1, 2, 3, 4, 5. Hey, I did it. I made another one. Put it the other way. It's like an ice cream cone kind of thing. So again, I believe this makes a continuous edge. That was 60 degrees here, and that was 120. 60 and 120 is 180, which makes a straight angle. Yeah, so that's one continuous side right there. All right, let's try to do my best to resketch that and add them up. So first, I had that hexagon. So hexagon looks something like this-ish. And then I continued like that edge up to make a triangle on top, something like that. Okay, so there's my shape right there. And then, well, let me make this a dotted line. Yeah, so that's, I'm gonna dot that out. So this is my shape, and again, let's just double check that I didn't confuse myself. 1, 2, 3, 4, 5 sides. And as far as angles go, let's use red. I have 1, 2, 3, 4, 5 angles. All right, so this one up here is a 60. And then I have 120, 120, 120, a whole bunch of 120s. So 4 120s and a 60. So 6, 7, 8, 9, 10, 11, 12, 13, 14. And and then carry the 154. Yep, 540 degrees again. All right, so we have two pieces of evidence that a pentagon has 540 degrees inside of it. So I'm going to attempt to make a bizarre pentagon, and you might want to try the same thing. So I have to just end up with 5 sides. So 1, 2, 3, 4, 5. That is a pentagon. Double check here. Angles. I have 1, 2, 3, 4, 5. Now I drew these lines at random, so measuring those angles is going to be a pain, even with a protractor. So what I'm going to do instead is I'm going to use that idea I brought up earlier about triangles. That what we can do is we can dissect a polygon into triangles by drawing a diagonal starting at one vertex. So we're going to dissect the polygon into non-overlapping non-overlapping triangles. So we start at a vertex to do that. So let's go over here and try. So which vertex should I start with? Well, it doesn't really matter. So I'm just going to say I'm going to start with this vertex right there. So what I want to do is connect that vertex to a vertex it's not connected to already. Well, this vertex is already connected to that one, so I don't need to do that, but it isn't connected there, so I'm going to connect those two. Still focusing on this vertex, it's not connected to that one, so I'm going to connect it. And it's already connected to that one, so I don't need to do anything about it. So now what I have 1, 2, 3 non-overlapping triangles here that completely fill this shape right here. And the interior angles of these triangles match the interior angles of this pentagon here. So let me just double check this with my highlighter. So I have this one interior angle there. These 2 interior angles make that big one. These 2 interior angles make that big one. That one interior angle is exactly the pentagon. And then the 3 triangles together at that vertex make up that angle right there. So what this shows me right here is I have 3 triangles inside here. And the interior angles of each of those triangles line up to build all of the angles of the original pentagon. So that means the pentagon must have 3 times 180 degrees inside, because each triangle has 180 degrees inside. So let's see, 3 times 180, that would be 3 times 100, which is 300. 3 times 80 is 240. 300 and 240 is 540. So basically what this triangle dissection thing is kind of a proof that any pentagon has to have 540 degrees inside of it because it is made up of 1, 2, 3 triangles. It's kind of mind-blowing that it doesn't matter how weird the pentagon is. If you pick one vertex to start the triangle dissection, it always works. All right, so if I do that up here, maybe I pick this vertex right there. It's not connected to that one, so I connect it. It's not connected to that one, but it is connected to the other 2 vertices, so I don't need to worry about it. So this is now 1, 2, 3 triangles. 3 times 180 is 540. Same thing here. I could start at the top there, connect it to vertices it's not already connected to. So I've now dissected this cute little pentagon into 1, 2, 3 non-overlapping triangles. 3 times 180 is 540. Isn't that beautiful? All right, so we're making progress. Let's go back here. So we've just discovered that a pentagon should have an should have an interior angle sum of 540 degrees. So I'm just going to put some sketches along to the side here, right? So this is, some of the work I've done here is reliant on other shapes. In particular, that inside of a triangle, there's 180 degrees. Quadrilateral is any 4-sided object. So that right there is a quadrilateral. And notice that if we pick on one of the vertices like this one and connect it to its non-adjacent vertex, I then split it into 1, 2 triangles. 2 times 180 is 360. If I take some arbitrary pentagon, switch color, there we go. 1, 2, 3, 4, 5 sides, and we pick on one vertex, then we should be able to make that into 3 triangles. Hexagon, similar. 1, 2, 3, 4, 5, 6 sides. Pick on any vertex, connect it to ones it's not already connected to. Then we should find it dissects into 3 triangles. So notice, 3 sides, 1 triangle. 4 sides, 2 triangles. 5 sides, 3 triangles. 6 sides, 4 triangles. So there's another pattern happening here that I'm going to try to keep track of. And that's just going to be number of triangles. And those triangles have to be, they can't overlap. They have to completely fill the inside, like tiling a floor. So number of triangles. So a triangle obviously has 1. A quadrilateral is made up of 2 triangles. A pentagon can be made up of 3 triangles, and a hexagon can be made up of 4 triangles. And we might guess, man, that looks awesome. So a 7-sided one must be made up of 5 triangles. Let's build a 7-sided shape. Now, warning, I should actually give this out for extra credit. If you can use these shapes right here to build a 7-sided polygon, a heptagon, do it and share it with me. I want to see it. I found I could easily make lots of gons, but a 7-sided one was challenging. So I think I'll send that out to everybody. I'll make a little reminder for myself to email the group. So pattern, block, heptagon. Okay, so I am not going to make my heptagon here. I am going to make it on my paper here instead. Maybe. There we go. So heptagon, aka a 7gon, 7 angles, 7 sides. So I'm going to try to draw one. If you could play along and draw yourself a heptagon. So let's see, I need 1, 2, 3, 4, 5, 6, 7. There's 1. I didn't mean, so this is convex because it caves, sorry, it's concave because it caves in on itself. I meant to make a convex one, so I'm going to try again. I'll get 2 of them. 1, 2, 3, 4, 5, 6, 7. Okay, so there's a 7gon there. So I have 2 different 7gons to play around with. And I'm going to use that triangle idea I mentioned earlier, where I pick a vertex, and it doesn't matter which vertex I pick. Maybe I pick this one right here as my focal point. And then what I do is I connect it to vertices it's not already connected to. So it's already connected by this edge here. So next I'm going to head over to that vertex because they're not connected yet. And it's not connected there, so I connect it. And when you do that, connect a vertex to ones it's not connected to already, you make a triangle dissection. All right, so what do we have here? When I make that vertex triangle dissection, I end up with 1, 2, 3, 4, 5 triangles. So then each of those triangles has 180 degrees inside, and that's going to give me all of my interior angles when I put those triangles together. So then what is 5 times 180? Let's see, 5 times 100 would be 500. 5 times 80 is 400. So that gives me 900. Did I do that right? Yeah, that looks right. 900 degrees. Let's double check with a different one. This one right here, let's double check it is a heptagon. It has 1, 2, 3, 4, 5, 6, 7 angles. Okay. And then what we do is we pick any one of those vertices here and we start connecting to vertices it's not already connected to by making diagonals only from one vertex. So there's one, there's one, there's one, and there's one there. I think I got them all. Okay, how many triangles did we make? We made 1, 2, 3, 4, 5 again. So it looks like whether it is concave or convex, reminder about those ideas back from section 1, this sucker right here is a concave because it caves in on itself. And this one right here is convex because it doesn't cave in on itself, heptagon. So it looks like every heptagon is made up of 5 triangles that don't overlap. 5 triangles have 180 degrees each, or 900 total. And I'm going to check this one more time in GeoGebra. I think we can do this there. Let's give it a try. So, a couple ways you can get to GeoGebra. If you just search for GeoGebra, and then let's see, actually, I skipped a step there because I've done this before. If I just search for GeoGebra, we'll get to the same page, GeoGebra. Either go to their main website or the geometry app. If I go to the main website, there's nothing wrong with their other apps. I want to choose the geometry one. The geometry one has just less clutter that we don't need. So they do have a calculator here and here. And the thing about the calculator, though, it comes with this grid, which sometimes is in my way. And usually with geometry, I don't want the grid most of the time. It just gives me this nice white to work with. And GeoGebra starts us off with this very simple set of tools: move, point, line segment, line, polygon, or circle. So I'm going to start with a polygon here. And polygon says just select all the vertices and then go back to the first vertex again. So I'm going to make myself a heptagon. So then I would just click 7 points. So 1, 2, 3, 4, 5, 6, 7, and then back to where I started. Okay. 1, 2, 3, 4, 5, 6, 7. If you had any trouble getting to the site, I'll put it in the chat and in the YouTube description. Once I have that drawn, I can then ask GeoGebra to measure some angles for me. And so it acts as a protractor. So I hit the More button, and then I'm looking around for measure angle. Not angle of a given size, that's different. We looked at that one last week too. I just want the angle. And the angle says to either select 3 points or 2 lines. The 3-point version, the middle point, the second point you click on is where the angle is measured. So if I click A, B, C, it's going to measure the angle coming out here from B. That's the central vertex of that angle. So to keep going around, and then I then go B, C, D, and then get D in the middle. C, D, E, and then get E in the middle. D, E, F, and we just keep working around like this, having GeoGebra measure these for us. And then we'll just have to move things around to see them better. There's a little overlap with the numbers and the letters. And you can always zoom in either with the wheel on your mouse if you happen to have a mouse with a wheel, or you've got these zoom in and out buttons over there. So I'm gonna zoom in and then move it so I can see it. And then sometimes I need to move these to better read them. So everything's grabbable if you click on the right spot. I found that when I tried to use this on a tablet, it was occasionally painful. And on my phone, forget about it. They do have a phone app, but it does some things good, but this would be hard to do on a phone. Then we just have to add up these numbers right here. So I would have to then whip out a piece of paper. So I'll just copy this into my notebook. So this is just some completely arbitrary heptagon. Let's add it to a new page. And so what do these add up to? So I've got 129, 139.7, 106.8, 121.2. Spreadsheet would be nice for this, wouldn't it? GeoGebra actually has a built-in spreadsheet, but I don't use it much. It's kind of an all-around math tool. Get something you want to do with math, GeoGebra can probably do it. All right, 1, 2, 3, 4, 5, 6, 7. All right, I got them all. Let's hope I can add, and the rounding doesn't mess up things. Sometimes there can be rounding error. So let's see, 7 and 8 is 15, 16, 17, 18, 19, 25, and 6 is 31. So we got a little bit of rounding error here. A couple things rounded up. So we have, let's see, 18, 19, 20, 21, 27, 28, 37, 45, and 5 is 50. We have 10, 11, 12, 13, 14, 15, 16, 20. And then 2, 3, 4, 5, 6, 7, 8, 9. So there's my 900 with rounding error. So it could be if I asked GeoGebra to show me the nearest hundredth or thousandth, I could get rid of the rounding error. But a couple of these rounded up and overdid the rounding just a little bit. So it should be 900, but again, there's a touch of rounding error. But I am close enough to that 900 for the heptagon that the other ones have. So, but just as important is back here, this triangle dissection pretty much proves that any heptagon can be carved into 5 non-overlapping triangles that cover exactly all of the interior angles. 5 times 180 is 900. So let's go put that in our notes page here. So heptagon, we found that there are 900 degrees in the sum of the interior angles. And I'm not going to redraw the picture, but the heptagon was made up of 5 triangles. Now, we have a pretty steady pattern here, so I'm just going to write what I think happens next. I think in an octagon, I think there's going to be 6 triangles that live inside of it. And is there a pattern going on in this list? How are these numbers jumping? And
They increasing by 180 degrees.
yeah, they're increasing by 180, right? You can see that pretty clearly in the first one right here. And if you just check, you can say, oh yeah, look at all the other ones keep increasing by 180, which kind of makes sense because we keep adding on a new triangle. A triangle has 180 degrees. So the next one, the octagon, should be 900 plus 180, which is going to be what, 1080? And if it's true that there's 6 triangles in there, we should be able to check that 6 times 180 is going to give us the 1080. So let's see, 6 times 100 is 600. And then 6 times 8 is 48, or in this case, 480. And there it is, 1080. Yeah, so there's 2 different patterns going on here that are both leading us to this number of degrees inside of an octagon. So let's make an octagon and double check to make sure this is true, that it's not too good to be true. Because it does happen in math that you discover this pattern, but all of a sudden later it just falls apart. It doesn't happen often. Is that true? It happens. All right, so let's see, heptagon, heptagon, octagon. So I'm thinking like a traffic sign. So I think I'll make this one red. So let's see, a traffic sign. Maybe I'll come up. That's not my straight line tool. Definitely need that today. And over, something like that. Over, back down-ish there. And I don't remember noticing this as a kid, but I'll point it out now. Let's see, I can show it back here. If you take a square and another square, and you rotate, just put that pen 45 degrees like that, and you stick them on top of each other, the overlap is an octagon. Kind of cute. So it's kind of like a double square star overlaps itself to make an octagon in the middle. All right, back, where was I? Here. So there's my octagon, and then the dissection, remember the way we do that is we pick some vertex, that one right there, and start connecting it to vertices it's not connected to. So it's already connected here, so I reach out to this vertex, and then I reach out to that vertex, and this one, so on until I run out of vertices to connect to. And it's already connected to that one, so I don't have to worry about it. And how many do I have? 1, 2, 3, 4, 5, 6. And this was kind of a regular octagon here, but this is going to work whether the octagon is regular, irregular, convex, concave. We're going to get 6 triangles. 6 times 180 is going to give that 1080 for the sum of the interior angles. So I think we're ready. Interior angles to come up with a formula, I hope. Let's give it a try. So back to our summary page here. So I have a couple of patterns that help here. And so I want a formula so that when I plug n into the formula, I do a little arithmetic and out pops the right answer. So if n were 7, for example, then the answer I should pop out of my formula will be 900, for example. If n was equal to 3, the answer should be 180. And there's a bunch of ways to think about this. One way to think about it would be, well, if we keep adding 180, there must be some multiplication by 180. So that ought to be in the formula somewhere. And over here, this is kind of telling me that, well, the number of triangles inside is important too. So if it had 3 sides, it has 1 triangle. 4 sides is 2 triangles. Is there a relationship between the numbers in this column to the numbers in that column over there? Like 5 to 3, 6 to 4, 7 to 5. So there's 2 different versions of this formula and they both match. So I'm going to go with the second version. So if I think about this, if I start with 5, but I need to turn it into 3, or I start with 6 and I need to turn it into 4, I think I just take away 2. So n is the number of sides. So one version of this formula should be to take the number of sides, take away 2 from that. Right? 6 minus 2 is 4. And then multiply that by 180. That's one version of it. Another version of it comes up here that I'm repeatedly adding 180. So that means there should be a multiplication. So thinking about it that way right there, let's see, maybe I'll do this one in red. There should be a 180 times n in there. Now, if I do 180 times n, that overestimates. Like 180 times 3 is going to give me 540. That's too much. Right? So 180 times 3 gives me 540. I really want it to be 180, so I adjust that. So let's see, if I picked, say, 6, 180 times 6, that would be 1008. I need it to be 720. So that's off by 2 180s. 2 180s is 360. So I'm going to just adjust it that way. So we played this kind of guess and check game with lists like this way back in Math 211. Guess repeated addition is multiplication, and then guess on how to adjust it by adding or subtracting. So I think I have two different versions of the formula, this one and that one. And I'm going to check them in two different ways right now. One way is if I just take this 180 and I distribute it through, 180 times 2 is 360 being subtracted. 180 times n is 180n. So that's good. So these two formulas match, but do they really work? Well, now I can check by doing something like plugging in n equals 7. So let's say I use this formula right here and I plug in n equals 7. I'm just going to check on my calculator. What's 180 times 7 minus 360? Oh, and Google, by the way, has a calculator hidden inside of it. Even if you use the geometry version, it records all the different things I did. But I can do a calculation. 180 times 7 minus 360 was the formula. And my calculator says that should be 900. And my notes say that should be 900. Check. Let's say I heard a ding dong, someone's at the door. Oh, looks like somebody must have left and come back.
It's me again. My internet's acting up at the school.
Oh, I'm sorry to hear that. I've had internet problems lately at home. All right, so we have just kicked in the pants, activity 10-2B.